everybody. In this DL, we started talking about the electric field. It's actually very closely related to what we studied last DL. We introduced the concept of a field in the last DL in the context of a temperature field. A temperature field was just a description of what the temperature was at every point in space. We called such a field a scalar field because the value of the temperature can just be represented by a single number. But the electric field is slightly different. It's what's known as a vector field. A vector field is still a field. It's defined at every single point in space. However, instead of just being represented by a number, as with the scalar field, a vector field has to be represented by a vector. It has both a value and a direction at every point. Let's look at the same example as we did last DL, just a single point charge. What is the electric field around this point charge? Well, to figure that out, we want to do a similar exercise to what we did last time. Well, we figured out last time that if we have a point charge and we know the voltage around that point charge, then we can determine the potential energy of a second charge placed at a point by multiplying the voltage from that first charge by the value of the second charge. The electric field is similar, except instead of potential energy, we're talking about force. If you know the electric field at a point, and then you place a charge down at that point, the strength of the force on that charge will be equal to the electric field times the value of that charge. So let's think about what the electric field around this point charge would be. What would happen if we put another positive charge here? Well, we know that like charges repel, and so these charges would just fly off in opposite directions. The same would happen no matter where we put it. Then the force on that charge would look like this. If we put a positive charge down here, then the force on that charge would look like this. And if we put a charge over here, then the force on that charge would look like this. So what does the electric field look like around this point charge? Well, the electric field just looks like the force diagrams. If we take a vector like this and multiply by a number, say the value of a second charge, we get another vector that points in the same exact direction. So the electric field from a point charge is just a bunch of arrows pointing directly away from that point charge. Let's draw that out. So this diagram represents the electric field around a positive point charge. Notice something interesting about the arrows. The farther away we get from the point charge, the shorter the arrows become. Why is this? Well, it's because of the way that the force between two charges works. The farther away that two charges are, the less force that they feel. And since we know that force and the electric field are directly related, the farther away we are from a point charge, the smaller the electric field will also be. A smaller vector is just a shorter vector. This arrow and this arrow point in the same direction, but this arrow is much larger than this arrow because we're starting very close to the charge. What would happen if we put a negative charge in this electric field? Well, we know that a negative charge will be attracted to the positive charge. But wait, you say, the electric field arrows are pointing out. So how can we go from an electric field that's pointing out to a force that's pointing in? The answer comes by thinking carefully about how the electric field and force are related. If we place a charge in an electric field, the force on that charge is given by the electric field multiplied by the value of the charge itself. But what happens if Q is negative? For example, if we place a negatively charged particle in this electric field. Well, if we take a vector and then multiply it by a negative number, its direction flips around. If we have an electric field that's pointing out and we multiply by a negative charge, we get a force vector that points in. Based on this, what do you think the electric field around a negative charge would look like? The answer is it would look exactly like this, except for one key difference. Instead of pointing outwards, all the electric field vectors would point inwards. One thing that's nice about electric fields is it allows us to determine how a particle will move, even if we don't know anything about how the electric field got there. One thing we like to do is try to draw paths that a charge might take if it was in an electric field. We call these lines field lines. Let's draw one on this electric field as an example. If we wanted to represent this electric field perfectly, we would technically have to draw a vector at every single point. But we can't do that, and that's another reason that these electric field lines are so useful. An electric field line gives us the overall shape of the electric field. Let's fill in a few others. These lines are nice because they allow us to see the shape of the electric field very easily. However, there is one big disadvantage to electric field lines. Remember that an electric field is a vector field. It has both a direction and a strength at every point. These electric field lines do a very good job of giving us information about the direction of the field, but they don't tell us anything about the actual strength of the field. You can think of these electric field lines sort of like an averaging over all of the vectors. Again, each of these two descriptions, the vector description and the electric field line description, have their uses, but we have to remember what information is available in which one. Let's go back to the point charge example one more time. What do the electric field lines around this point look like? Well, we already determined that the electric field points straight away from the charge. So the electric field lines will just be straight lines traveling outwards. Now let's draw something else. Remember last time we talked about equipotential lines. These are just lines that we draw so that all of the points on the line have the same voltage. Do you remember what those lines looked like around a point charge? Well, they looked like circles. Let's draw in a few of these lines and see if we can see a relationship between them and the electric field lines. Do you notice anything interesting about these lines? The electric field lines and the equipotential lines are always at right angles to each other. This turns out to be true no matter how complicated your setup is. The electric field will always point perpendicular to equipotential lines. Why is this? Well, before we answer that question, let's write down what we know so far. These are the things that we know so far. The potential energy of a charge is equal to the value of that charge times the voltage at the location that it's at. The force on a charge is equal to the value of the charge multiplied by the value of the electric field at the point that it's at. And lastly, we also know that the force on an object is equal to the negative derivative of the potential energy with respect to position. Let's ask a question. If we start on this purple line and move the charge around the purple line, then what is the change in potential energy? Well, the answer is 0. The purple lines represent locations where the voltage is the same. If the voltage is the same at all those locations, then the potential energy of a charge at those locations would be the same as well. So if we move the charge around one of these circles, there's no change in potential energy, and therefore there's no piece of the force that points in that direction. However, if we move our charge along one of the black lines, the potential energy does change. So we know that the force has to point in that direction. As I said, this will always be true, no matter how complicated your setup, for the exact same reason. So we know these two, and the last thing we want to ask is, can we figure out a relationship between voltage and the electric field? This should suggest an answer. What is force? Well, we know that the force is equal to the charge times the electric field. And we know that the potential energy is equal to the charge times the voltage. So what happens if we replace potential energy here with charge times voltage? Well, the charge is constant. It's not changing. So we can just move it out of the derivative. That looks like this. Since there's a Q on both sides of this equation, we can just erase it. Now, I don't want to spend too much time thinking about the calculus here, but I do want to summarize what this equation says. The equation says that the electric field will always point in the direction of changing voltage. If moving in a particular direction does not change your voltage, then there will be no piece of the electric field pointing in that direction. Let's again think about the example here. As we move around one of these purple circles, the voltage is not changing. That's just what these purple circles represent. They're locations where the voltage is always the same. So, since the voltage is not changing in that direction, then there is no part of the electric field that points in that direction. So, as we know, the electric field just points straight out. I know this might feel like a lot of information, but we can sum it up in a few key points that will help us as we're moving forward. First, the potential energy of a particle in a particular electric field is given by the value of that particle multiplied by the voltage at that point. The force that an object will feel, if it's an electric field, is just equal to the value of the charge multiplied by the electric field itself. Equipotential lines and electric field lines will always point perpendicular to each other, no matter how complicated your setup. This is because the electric field is directly related to the change in voltage as you move around. If there's no change in voltage in a direction, then there's no electric field in that direction. The only other thing we have to think about with electric fields is what happens when we put them together. We actually already know how to do this. Electric fields are vector fields, and we know that we can add vectors. So for example, if we have an electric field that points this way here, and then we add on an electric field that points this way, then if we add the two together, we'll just get an electric field that points straight up. In the next TL, we're going to start seeing how we can use this information to attack some interesting problems. One of the things that's nice about electric fields and equipotential lines is that they're very visual, and you can always draw them as long as you follow the rules that we've talked about. And we'll see how that works in the next DL.